Hello, in this video I'm going to solve the following problem for you. This is problem 2.38 from the book Introduction to Quantum Mechanics, 2nd edition, written by David J. Griffiths. Let me read the problem together first. A particle of mass m is in the ground state of the infinite square well. Suddenly the well expands towards its original size, the right wall moving from A to 2A, leaving the wave function momentarily undisturbed. The energy of the particle is now measured. Part A. What is the most probable result? What is the probability of getting that result? Part B. What is the next most probable result and what is its probability? Part C. What is the expectation value of the energy? Hint: if you find yourself confronted with an infinite series, try another method. I recommend you to pause the video at this point and try to solve the problem yourself first. If you do the calculations right, the answers that you will get are as follows. For part A, we will see that the most probable energy is E sub 2 equals to pi squared h bar squared over 2ma squared, and the probability that this energy is measured is 0.5. For part B, we will see that the next most probable energy is E sub 1 equals to pi squared h bar squared divided by 8ma squared, and the probability that this energy is measured will be 32 over 9 pi squared. And finally, for part C, we will see that the expectation value of the energy, or the Hamiltonian of the system, becomes equal to pi squared h bar squared 2ma squared. Okay, so I have gathered the information that is needed for this problem. If you have studied the infinite square well in that book yourself, you will see that by infinite square well, whose width is from 0 to a, we mean a potential like this, which is 0 if x is between 0 and a, and it goes to infinity beyond this interval on the left-hand side of 0 and after that a. Yes? And this information actually that I have written here, I have extracted from the book, chapter 2, and then let me just read it here for you. You'll learn that the energies of this system are quantized, and the values for the energy are given by this formula: n squared pi squared h bar squared divided by 2ma squared, where n is a natural number starting from 1. And then the solutions to the time-independent Schrödinger equation corresponding to this potential are given by this formula. So it is a square root of 2 over a. Of course, this a that appears here and there are actually this a. This is the width of the well, and then you have a sine function here. The only deviation that I have made from the one in the book, I have changed the letter psi to phi, and I have changed the energy E to curly E here, because I want to distinguish between, because here apparently we are facing two infinite square wells. So this is why I want to reserve the letter psi and capital E for this infinite square well of width 2a. Of course, in principle, this problem is just one problem, and that is an infinite square well of width 2a. So the only thing that we have is this. For my system, my initial wave function, from what we understand in this problem, we learned that the initial state for my particle is the ground state of the infinite square well of width a. So it means that this can be translated itself into this in mathematical formulation, that the initial state for me is phi 1x, and of course here I can replace n with 1 and I get my function. So this becomes square root of 2 over a, and then I will have sine pi x over a, x between 0 and a, and then I will have 0 otherwise. Okay, now I am measuring energy, and then I want to see that what are the probabilities more or less about finding those values for energy. But of course, we need to know what are the allowed values for energy. That is simple, yes? So this is what is happening, by the way. Let me draw a picture for you here. So what happens is initially my wave function is this. So if I want to draw it, it is 0 if I am beyond this interval. So it means that here this is 0. Before 0, the function is again 0. And then between 0 and a, I have an arc, which is represented by a sine function. And it is clear that if x is a over 2, then this becomes pi over 2. Sine pi over 2 is the maximum value that sine can get. So it means that it reaches to its maximum when x is equal to a over 2, something like that. And of course, if you want to find this maximum is nothing except square root of 2 over a. So, and then exactly at this moment, this wall actually expands to this one. So this means that I do not have this anymore from now on. So in principle, I am facing an infinity square well of width 2a, not width a, but the wave function, initial wave function, is this orange curve that you can see here. Okay, so it means that now if I ask you, do we know energies of this system? It is clear, yes. The answer is yes. So let me change my color. So now the potential that I have is just this potential, again 0, but this time x is between 0 and 2a, and infinity otherwise. And then if I ask you, what are the states? The states are exactly these functions. The only difference is that I have to change a to 2a wherever I see a, yes? So if I change a to 2a, 2 and 2 are cancelled. So then I will get 1 over a square root of a, and then I will get sine n pi x over 2a, where x is between 0 and 2a, and 0 otherwise, yes? And if I ask you, do I know energies of the system? You would say yes. The energies, let me show them by En, are n squared, pi squared, h bar squared, divided by 2ma, but instead of a, I have to write 2a. And 2a squared becomes 4a squared, multiplied by that, it becomes 8. So it becomes 8ma squared, but again, n goes from 1, 2, 3, etc., etc. So this is now my situation. So I already know what are all possible energies. I don't need to calculate anything. I know all possible energies, and I know the solutions to the Schrödinger equation corresponding to this wave function. What I want to calculate is to calculate the probabilities of getting these energies. So for each particular value of n, I need to know what is the probability of getting that particular value for energy. And then if you remember, if you want to do this, I have to expand my initial wave function, as a linear combination of these states, yes? So I would write Cn, and then psi nx, n goes from 1 up to infinity here. And then I need to find these Cn's. Why? Because if I want to calculate the probability that a measurement of energy gives me the particular value En, this becomes equal to this coefficient, absolute value squared. So in principle, what I want to do, I want to find these coefficients so that when I plug these functions here and I add them up, it gives me this function back. And that is actually very simple to do. So instead of psi, x and 0, I put phi 1. So let me write it here for you. So then it becomes phi 1, x equals to sigma Cn psi nx, n goes from 1 to infinity. And then I want to find psi n, and hopefully you remember the trick. So let me repeat here. I multiply everything by psi m star x and then phi x, and then I integrate from minus infinity to infinity always. I will do the same thing here. So I multiply this by psi star. So let me write Cn first. Psi star m x psi n x, and then integrate from minus infinity to infinity. And this is a constant, so I can pull it out from the integral and I will get this situation. Of course, so you know that in Griffiths you have seen that these functions have this property that they are orthogonal, meaning that this expression is nothing except a chronicle delta. So this is delta mn. Delta mn, it is equal to 1 if m is equal to n, is 0 if m is not equal to n. So this means that from all this sum, only one term will survive, and that is the term corresponding to n equals to m. Yes? So this means that I will get this formula. So on the right hand side I will have Cm, so let me write it here. Cm is equal to the integral from minus infinity to infinity, psi m star x phi 1x dx. Yes? So I got this formula for any natural number m, but usually we denote the index by n. So if you don't mind, let me just clean this. Instead of m, now I can write it n. And now I do not need this star for this particular case because my functions are actually real. So I can also clean this one for this particular case. And now what I have to do is to calculate this integral. Okay, so here if I want to calculate this integral, it goes from minus infinity to infinity. So I break this integral to several pieces. Okay, so I have to write this equals to, let me write here, this becomes an integral from minus infinity to 0. So let me just ignore writing the integrands for the time being. And then it goes from 0 to a, and then it goes from a to 2a, and then I finally break it from 2a to infinity. Yes? But now let us see what is happening here. The first integral will be 0, because if x is less than 0, both this function is 0 and this function is 0. So this means that this will vanish. Yes? The first integral vanishes. What about the second integral? When x is between 0 and a, this phi does not vanish. So you see the phi 1 does not vanish, and this one does not vanish. So this will survive. Yes? But from a to 2a, still psi n does not vanish, but psi 1 vanishes. So this means that this also vanishes, and for the same reason, this also vanishes. So it means that I am left with only one integral. So let me write it down for you. So this becomes integral from 0 to a, psi nx. What is psi nx? Is this one. So it is 1 over square root of a sine n pi x over 2a multiplied by phi 1. Phi 1 is this one. So the square root of 2 over a sine pi x over a dx. So you need to be careful. This is a little bit strange because the width of the infinite square well is 2a. You might expect that you have from integration limit from 0 to 2a, but as you see, according to what I explained for you, integration is going from 0 to a. So let me simplify this and write it here. So Cn is equal to square root of a is a, and I have a square root of 2 up there, so it becomes square root of 2 divided by a. An integral from 0 to a, I have two sine functions multiplied. So n pi x over 2a, and then I have sine pi x over a dx. So this is the formula that I get for these coefficients. But this is a standard integral. I have to calculate this integral. And this is the product of two sine functions, and we have this famous trigonometric formula that sine of alpha multiplied by sine of beta can be written as the sum of two cosine functions. 1 over 2 cosine alpha minus beta minus 1 over 2 cosine alpha plus beta. Yes, so that is the trigonometric formula which is well known, and I use this here for this integrand. So then it becomes Cn is equal to, so if you see I have a factor of 1 over 2, 1 over 2, I pull that factor of 1 over 2 here, and then simplify it with that square root of 2, so it becomes 1 over a square root of 2 in the denominator, and then what is left for me, let me write it in this form, it becomes integral from 0 to a. Here, I give the role of alpha to this, I give the role of beta to this one. So then what happens, this becomes cosine alpha minus beta. Okay, so what can I do? I can factor pi x over 2a out, and then from this one, only n is left, and from this one, 2 is left. Yes, so let me put this in the square brackets, not to get confused. So you see, if I multiply this back, it becomes n pi x over 2a, which is exactly alpha. And if I multiply this there, these 2 and that 2 are cancelled, I will get beta back. And that's exactly alpha minus beta, yes? And then I have minus, so let me write them in two integrals. So it becomes minus integral from 0 to a. This time I will add them, the only difference that I will have a positive side here. Cosine n plus 2 pi x over 2a, yes, dx. Okay. And we want to calculate these two integrals, which of course are cosine integrals and a standard. But there is a very delicate point there, and you have to be careful about that. So apparently we have two cosine functions, but this one needs more attention. Why? Because you know that n is a natural number, 1, 2, 3, etc. I do not have any problems here because whatever I choose for n, this is not vanishing, so I will always face a cosine function, and I know that the integral of the cosine function is a sine function. But this one is always a cosine function with one exception, and the exception is that when n becomes 2. Yes? If n is equal to 2, then this argument is 0 and cosine of 0 is 1. No longer, I do not have any cosine function any longer. Yes? So I have to solve this problem in two, by separating n equals to 2 and n not equal to 2. Yes? So let me consider the case where n is equal to 2. Yes? First, let me consider this case first. So then instead of n I put 2, so c2 becomes 1 over a square root of 2, and then here I will have integral from 0 to a, n is 2, so cosine of 0 becomes 1, so it becomes dx, minus integral from 0 to a, n is 2, so it becomes cosine, 2 and 2 are simplified, so it becomes 2 pi x over a, dx, yes, because 4 and 2 are simplified. But this integral is simple to calculate, so it becomes 1 over a square root of 2. This integral is nothing except a, and this integral becomes minus a over 2 pi sine 2 pi x over a. X goes from 0 to a. But then you immediately realize that the second term here vanishes, because if I put a here, a and a are cancelled, sine of 2 pi is 0, and if I put 0, sine of 0 is also 0, and then this will actually vanish out. And then what happens, what is left for me is a, and then if I multiply that a, I will get exactly a square root of 2. So this will imply then that c2 is a very simple number, 1 over square root of 2. Okay? Here, at least, I can calculate the energy E2, the probability that I get E sub 2. It is C2 absolute value squared. So let me write this one here as well. So this means that the probability of getting energy E2 is equal to this number squared, which is 1 over 2, 0.5. Yes? And what is E2? If I ask you what is E2, you need to put 2 in this formula. And then it becomes 4, and this one simplified. So E2 is exactly pi squared, h bar squared, divided by 2ma squared. Yes? So we realize that with probability 0.5, I will get this energy when I measure the energy of the system. But still it is not clear that this is the most probable one. According to the answer, this should be the most probable one. But it is not clear yet. So I have to consider another scenario to see what will happen here. Okay, so I can go up to here. So now let us consider the case or the cases that n is not equal to 2. And then in that case, I have to go back and do it in these two integrals again. So Cn becomes equal to 1 over a square root of 2. This first integral becomes 2a over n minus 2 pi, and then cosine becomes sine. This goes from 0 to a. Yes, let me double check. Yes. And then the next one is negative. I will have 2a, the same thing, but n plus 2 this time. And then I have sine of n plus 2 pi x over 2a. It goes from 0 to a again. So this would be my Cn, of course, if n is not equal to 2. Okay, so let me try to simplify these things a little bit. So you see that I have a 2a and a pi here. I can factor it out. So that 2 will make this one square root of 2 in the numerator. That a, that will cancel this a. Then I will get 1 pi here in the denominator. Okay, and then what is left for me here? This is 1 over n minus 2. And then here, if I put a here, this a and this a are cancelled. So it becomes pi over 2. I multiply pi over 2 inside. So it becomes sine of n pi over 2 minus pi minus, I will have 1 over n plus 2 this time. But again, I didn't put 0, because I put 0, of course, sine of 0 is 0, so I didn't actually counted on it. Here, the same story. If I put a, it becomes pi over 2. Pi over 2 multiplied in, it becomes pi over 2 n pi over 2. And then I will have plus pi. And if, of course, put 0, nothing happens here. So that is actually my coefficient Cn. But let me simplify these two things here. This expression is minus sine of pi minus n pi over 2, and this becomes exactly equal to minus sine of n pi over 2. And if I ask you what is this one, this is just a simple trigonometry, yes? Here, this becomes minus sine of n pi over 2. Okay, so Cn becomes equal to, this is minus minus, so it becomes plus. So let me write that plus one first. I will have square root of 2 over pi. And then I will write 1 over n plus 2. Yes? And then this one becomes negative 1 over n minus 2. And of course, sine n pi over 2 in this term and that term are in common, so I can factor it out, for example, here on the right-hand side. Yes? So double check. This minus sign makes it positive. This is why I have written it here. This minus sign remains, so this becomes negative, and everything is in order. And I think it is also better to take the common denominator here. If you take the common denominator here, it becomes n minus 2, n plus 2, yes? So this becomes n minus 2 minus n minus 2 is minus 4 square root of 2 pi, and the denominator is n squared minus 4. Then you have 1 here, then you have sine n pi over 2. Yes? So these are the coefficients Cn if n is not equal to 2. Okay, and then I can calculate Cn squared. So the probability of getting En, if n is not equal to 2, of course, Pen is equal to absolute value of this expression squared. So if I take the absolute value this and square it, it becomes 32. And then this becomes pi squared. Then I will have sine to the power of 2 n pi over 2 divided by n squared minus 4 to the power of 2. So that would be the probability of other energy levels if n is not equal to 2. Okay, we want to calculate the most probable result, the most probable energy, and the next most probable energy. Okay, so let me calculate PE1 because we have already calculated the probability for E2. So what is PE1? Yes, PE1, this one becomes sine of pi over 2, which is 1. So this becomes 32. And then this one becomes minus 3 to the power of 2, 9. So 9 pi squared. So this is the probability of getting energy E1. What is energy E1? Energy E1 is calculated from here by substituting 1 for n. So it becomes pi squared h bar squared over 2ma squared. So you see that with probability, this number, I get this amount of this value for energy, and with probability 0.5, I get that value for energy. But of course, it is very simple to see that 0.5 is a higher probability, yes? 0.5 is 1 over 2. Let me change my color. 1 over 2. I'm claiming that 1 over 2 is larger than this one, yes? And that is completely true because this becomes 9 pi squared greater than 64. We know that this is true because pi squared is close to 10, so it's 90. So that's clear. So that is clear that 1 over 2 is larger at least from PE1. So between the competition of this one and that one is actually winning. But there are many other ones left. We have to convince ourselves if that value, according to the answer that I read for you, if this is going to be the most probable one, I have to be able to convince you and myself that 0.5 is the largest Cn squared. Yes, how should I do that? But that is also simple. So if n is greater than or equal to 3, let us try to estimate this. We know that this number is definitely less than or equal to 32 pi squared 1 over n squared minus 4 to power 2, because sine squared n pi over 2 is at most 1. So definitely this one is less than or equal to that one. Okay? But now n is greater than or equal to 3. So it means that this one is also less than or equal to 32 pi squared. If I want to make it bigger, I have to choose the lowest value for n because the denominator should be smaller. And if I put 3, it becomes 1 over 25. Yes? 9 minus, yes, that's correct. So this means that if n is greater than or equal to 3, P of En is definitely smaller than this number. Yes? And of course, this number is definitely smaller than this number, okay? And we learned that this number is also smaller than 0.5. So then it becomes clear that 0.5 is the highest probability, and the energy which is mostly probable for us to get is E2, and the next probable result is E1, whose probability is this one. Yes? So in this case, we were able to solve the first part and the second part of this problem. Now, according to the last part, if you know, there are two methods to calculate the expectation value of energy. Of course, they are equivalent mathematically. So one method is this one. So expectation value of the Hamiltonian is sigma. Here, n goes from 1 to infinity, Cn squared En. Yes? And that is exactly, if I want to follow this, that is exactly what Griffiths asked us not to do. So if you find yourself confronted with an infinite series, try another method. But let me momentarily put these values here. So what happens? So this becomes sigma, n goes from 1 to infinity, and Cn squared. All of them, so you see that if I want to solve the problem, I need to write it in this way. If you really want to do that, instead of this one, you need to write C1 squared E1, and then you need to write C2 squared E2, and then of course from now on you can write sigma from n equals to 3 to infinity, and then you write Cn squared E2, En, yes? Okay, but C1 is this number. C1 is actually this number. C1 squared is this number, so it becomes 32 over 9 pi squared multiplied by energy 1. So it is pi squared h bar squared divided by 2ma squared, yes? And then the next one becomes C2, which is that number, 0.5. So, yeah, that is 0.5, so let me write 1/2. And then E2. E2 is pi squared, h bar squared, and then I have 2ma squared. And then of course plus sigma, n goes from 3 to infinity, and then instead of absolute value of Cn squared, what can I write? I can write this expression squared. That is exactly what I have here. So it becomes 32 over 9 over pi squared, and then I will have sine squared n pi divided by 2 divided by n squared minus 4 divided by to the power of 2. Yes, so that would be the expectation value, multiplied by En, which is n squared pi squared h bar squared divided by 8ma squared. Yes, it's on the board. So this would be my expectation value for energy, but of course, according to Griffiths, we want to avoid that, even though that is technically right. So another way to do this is to use this fact that expectation value of the Hamiltonian does not depend on time. So if you want to calculate, you can just calculate it as before. So you can just write your state, Hamiltonian applied on it, and then an integral. So if you can calculate this integral, then you are done. Okay, but what is psi of x and 0? Psi of x and 0 is this expression, so that is nothing except phi 1. Okay, and then you know that phi 1 vanishes if I am outside 0 and a, so this integral reduces to integral from 0 to a, not to a, even though we are solving the infinite square well for width to a. So this becomes phi 1, and I don't need to put a star there because that is real. But what is my Hamiltonian? My Hamiltonian is minus h bar squared divided by 2m, the second derivative with respect to x squared, and plus my potential. Potential in this interval is 0, so I don't need to write anything, and then I have to multiply it by psi x and 0, which is phi 1 again, so it doesn't hurt if I write phi 1 right here and then dx. So what I can do, I can calculate this integral. So here I will get it and write it in this form. So it becomes minus h bar squared divided by 2m, integral from 0 to a, phi 1, it becomes square root of 2a, 2 over a, phi 1 is sine pi x over a, and then I have to take second derivative of this function. Yes? For if I take the second derivative, I will get another factor of 2 over a. But when I differentiate first, and a factor of pi over a goes out, and differentiate once more, a factor of negative pi over a goes out. So it becomes negative pi over pi squared over a squared. But then again, it returns back to sine, the same sign, yes? So it becomes sine to the power of 2, and then it becomes dx. So I differentiate that function 2 times. Okay, so then what happens if I want to simplify things? So you see, I have square root of 2a coming out, this minus sign and that minus sign are cancelled. So let me write h bar squared, and then I have pi squared. Here I have 2ma squared, and then I have 2 over a. Yes? And then I want to calculate integral from 0 to a of sine squared, but that's also a standard integral, so I have to use this formula. Sine squared of any angle alpha, I can write it 1 over 2 minus 1 over 2 cosine of the double angle. Yes? So I use that trick. So what happens? It becomes 1 over 2 minus 1 over 2 cosine of 2 times this angle, which is 2 pi x over a, and then dx. Yes? So let us simplify things. These 2 and that 2 are cancelled. So what is left for me is h bar squared pi squared, and then I have ma cubed. Yes? But then the integral of 1 over 2x is 1 over 2. 1 over 2 is 1 over 2x from 0 to a. It becomes a over 2. But this integral becomes a sine function from 0 to a. For both of them, that becomes 0. So that is the end of the problem. And then I would write this a and that a are simplified, so it becomes pi squared h bar squared divided by 2ma squared. So that is the exact expectation value that I get from here. Okay, so that is a very nice thing. Now you can say that, of course, if we have done everything right, this infinite series, the sum of this infinite series should be equal to this expression. And if you put this one equal to that one, then you can use quantum mechanics to find the sum of this infinite series. Yes, just move this to the other side, simplify things, and then you can cancel the unnecessary factors, and then you get an infinite series here that you see is equal to something, yes? Is equal to a number that is calculated using this. So you can call it the application of quantum mechanics in finding the sum of the sets. Okay? Okay, I hope that this video is somehow useful for you. Until the next video, be safe and goodbye. Thank you.